You've created a bunch of really cool shaders, but your frame rate is really slow. What do? Watch this video. Today we're going to cover the topic of measuring and optimizing shader performance. First, let's talk about measuring performance. There are three main ways that we can use to measure the performance of our shader. The first one we can use here in our scene view. It's called a view mode, and we can go under Lit here and come down here to Optimization View Modes and select Shader Complexity. And what this view mode is going to do, I know it's kind of this crazy blinding green, but you can see you've got this gradient down here at the bottom. And what this does is shades all of the objects in your scene along this gradient from green to white, depending on how complex the shader instructions are. So you can fly around your scene and look at all the objects. If things are green, that generally means the shaders are pretty cheap. And the closer to white they get on this gradient, the worse they are. So we can see we have one object here that's hovering kind of around here in this maroon area. So if we wanted to, we could go in and optimize this. So that's one method of measuring shader performance. However, this method is not perfect, and while I discuss this, I'm just going to turn it off so I don't blind you guys. This method of using the viewport performance view is not perfect because it only gives you a very general idea of which shaders might be more expensive than other shaders. And also, this gradient depends on the number of instructions in your shaders, which is also not a perfect method of measuring performance. But let's get into that next. So the next method of measuring viewport performance is by checking the number of instructions that your shader takes. So here I've got my shader, and down here at the bottom you can see it says base pass shader 115 instructions. Well, what does that mean? Our shader node graph here compiles into HLSL code, which is then itself compiled into assembly language instructions, which are then passed to the driver and then passed to the video card. So if you know how many assembly language instructions your shader takes to run, that's another way of judging roughly how expensive is this shader. So in this case, my shader is taking 150 assembly language instructions. So if I were able to reduce my instruction count, I could probably safely assume that running fewer instructions would result in a shader that would perform better. However, using shader instructions as a measurement is not a perfect method either, because not all instructions take the same amount of time to run on the GPU. So you might have one instruction that takes 10 hundredths of a millisecond and another instruction that only takes 2 hundredths of a millisecond. And so there would be a really big difference if you had a shader that was mostly made up of the first instruction rather than the second instruction. So you can see that knowing the instruction count of your shader is not necessarily the perfect method for measuring performance. The third method for measuring performance, and this is the best, most accurate method, is to apply your shader to the model that it's intended to be in, put that model in the scene where it's going to be in your game or your project, and then run that game or that project on the intended target platform and measure that way. Now, measuring this way is the hardest because you have to apply your shader to a model, put the model in the scene, put the scene on the platform. There are a lot more steps involved, but it's definitely the most accurate. Every platform, whether it be the PlayStation, the Xbox, the PC, whatever game console or hardware you're running your shader on, is going to have different hardware capabilities, and every shader is going to behave slightly different depending on what hardware you're using. So measuring the performance of your shader on the target platform in the scene where it's going to be used is the most accurate way of doing it. And so when you're finaling your project, you definitely want to do it that way. But in the meantime, when you're just building your shader, instruction count is a pretty good way of judging relative to other shaders how complex or simple is this shader is it going to be. So today we're going to focus mostly on using instruction count and try to reduce our instruction count as we optimize our shaders. Okay, so we talked about the performance view mode, we talked about shader instruction counts, and we talked about measuring your scene on your target platform. And it kind of goes in order. So the performance view mode is the least best method. Judging instruction counts is probably the second best method, and then measuring your scene on the target platform is the best method for measuring performance. Okay, well, let's jump right in and talk about a few different ways of optimizing your shaders and improving the performance of your shaders. Today we're going to talk about 3 different methods of, well, actually, let me throw in one more method. We're going to talk about 4 methods of optimizing your shader. The first method is just to remove things. So if there are things in your shader that you're not using, if you're sampling textures that are just completely black and they're not contributing anything, if you're doing a bunch of math but the math results in a value of 0 and you can just throw it away, you want to go in with an axe and chop your shader and get rid of anything that's not used. A lot of times I've seen people that will create like a really complicated shader and then turn off a bunch of the features and only use 2 or 3. And a lot of times those things that they've turned off, in air quotes, are actually contributing to the expense of the shader even though they're not doing anything. And so you want to make sure that your shader is doing exactly what you want it to do and not more. So if there are extra features that you're not using, be sure to remove them. So that's the first thing that you want to do when you optimize a shader. The second thing that you can do is refactor your math and use different methods of arriving at the same result. So here we have our environment blend shader that we created in a previous video. And if you want to, you can go and check that video out right here. I'll put the link here and also in the description below, so you can see how we built this shader. But let me go over it just briefly here. We've got a rock material and a moss material. So we have a rock diffuse texture and a moss diffuse texture, and then our normal maps for our rock and our moss. And we're blending between these two based on a mask that points upward in world space. So these nodes right here are what create our mask. This guy gets our normal in world space, and then we take our Z component of the normal, which in Unreal is the up vector, and then we adjust that by adding to it, raising it to a power, and clamping. Now this power node right here is intended for increasing the contrast in the shader. So if we just take a look, I'm going to wire this into our base color so we can look at what that looks like over here. And I'm going to switch this to unlit so that we can see. So you can see there's a really sharp line between where a mask is white and where a mask is black. And that's being done by our power node here. So let's see what happens if we set power to just 1. It's going to refresh here, and you can see that as I move this around, there's a lot less sharp gradient. So there's a bit. So here we have white, and then it goes to gray, and then to black. So if we're not raising to a power, we have a smooth gradient. But did you also notice that when I reduced my power to 1, the amount of the mask moved way down the sphere here? So it also adjusted where it was being applied. So this node here is used for adjusting the contrast, but it's also affecting where the mask actually shows up. And so what we want to do is, I happen to know that this power node is one of those shader instructions that's a little bit more expensive than others. So we want to try to replace this power with something else that can adjust our contrast, but also something where we can adjust it without it changing the position of where our mask is applied on our object. And so what I'm going to do instead of using power is, let's say we have our range going from 0 to 1. That's our mask. That's what we can see here. Actually, I'm just for a minute, I'm going to wire this part of our shader into the view so you can see, like, without any contrast adjustments, this is what it's going to look like. So I'm going to take that, I'm going to subtract 0.5, and so now our range is from negative 0.5 to 0.5. Then I'm going to multiply by some value, and this is the value that I can use for sharpening the edges and increasing the contrast. And then I'm going to add back my 0.5. And what these three nodes do together is, when I shift my value from a range of 0 to 1 down to a range of negative 0.5 to 0.5, now when I multiply this, it's pushing values away from 0. So anything I multiply is going to, if my value is 0.5, it's going to stay right in the middle. But if it's higher than 0.5, it's going to push it up toward the top end of the range. And if it's lower than 0.5, it's going to push it further toward the bottom end of the range. And then I'll add this back, so now I've increased my contrast, pushing it toward the top or the bottom, and then I've added it back, so now I've shifted it back so my range is again between 0 and 1 again. And then I'm going to clamp it just to ensure that it stays there. So let's wire this up here into our base color and see what our mask looks like. So our mask looks exactly the same, and that's because I'm just multiplying by 1 here. But if I raise my multiply, let's multiply by a value of 20. And now you can see that we've pushed our mask and it's doing what we wanted. We've sharpened up these edges, so it's no longer a nice gradient slowly moving from 0 to 1, but now it jumps immediately from black to white. So that's pretty cool. So we've got something that does something similar to power in changing our contrast, but it's a little bit cheaper. Now let's put our shader back together so I can show you the difference in performance. So I'm going to wire this lerp back into base color, and I'm going to use this mask here. Whoops. I'm going to wire this mask here into our lerps instead of this one. And so the shader will compile, and now you can see it's 111 instructions instead of 115 like it was before. So let's go back to the previous version. So using the power node and a clamp is 115 instructions, whereas using subtract, multiply, add and a clamp is only 111 instructions. And that's really interesting because you would think that using 3 nodes would be cheaper than using 1 node. But in this case, raising something to a high power is a fairly expensive operation to do, and we can do it more cheaply if we just subtract, multiply, and add. And like I was saying before, the other benefit to our subtract, multiply, add is that now we can adjust how much contrast we get here without our mask moving up and down the sides of our model. So, no matter what I set this number to, my mask is going to stay in the same place. You can see here that the mask is a nice transparent gradient, but it's still roughly in the same place in the model. I can set this to like even as high as 100, and the mask is still going to maintain its position on the model. It's just going to be sharper, so there's really defined lines between my top mask and my bottom mask. Whereas if I use this one, I can adjust my power here, but did you notice how it jumped up to the top? So my power is at 20. If I set my power to 100, it'll be even sharper, but the mask will recede further and further up to the top of the model. If I set it down to something like 2, for example, you'll see that it'll come down and be down here instead. And that's not what we want. So using this is both more efficient and more useful in our shader to increase our contrast. So if you can figure out alternate ways of doing things and replace expensive instructions with cheaper ones, you can create a more efficient shader. Okay, let's take a look at another example of rejiggering our math to make our shader more efficient. This is our Atlas walk example. So we built this shader network together in a previous video where we were talking about flipbooks, and we talked about how Unreal has this flipbook node built into it, and then we built this shader which creates our flipbook animation, and we did this one ourselves instead of using the built-in one. So if we look down here, you can see that we have an instruction count of 100. So this shader that we built has an instruction count of 100. Let's take a look at what our flipbook node will give us. So if we use the flipbook node that's built in, it gives us an instruction count of 98. Well, I took some time and went through what this shader was doing and looked at what the flipbook shader was doing as well, and I came up with another set of nodes that does the same thing as this shader but does it more cheaply. So basically doing the same math, but I refactored the formula. So I'm going to take this and wire that into our texture sample, and let's see what our instruction count ends up with. So here we've got an instruction count of 97. So this set of nodes for doing a flipbook is as cheap as I can get it, 97. So we started out at 100, and then the built-in method was giving us 98 instructions, and this new method that I created is giving us 97 instructions. So it's just showing you that you can shave off just a little bit by refactoring how your math is done to save yourself a little bit of time. Now, one instruction may not seem very much, but if you've got this covering your whole screen, or if you've got tons of shaders and you're able to shave just a few instructions off, you may be able to save a millisecond or two on your performance, which is big. Which can result in several frames per second better performance for your players, and that's the end goal. Alright, let's take a look at another method of shader performance, and this method I like to call pipelining. And we're going to take a look at the distortion shader that we made in a previous video. What this shader is doing is it's sampling a couple of textures, and it's using the noise in those textures to distort the UV coordinates and then look up into a third texture. And you can see here that this section of our shader and this section of our shader are basically duplicates. The only thing that's different about these is the numbers that we're passing in to multiply our time value with. So here we've got 0.34 and 0.12. And here we've got 0.13 and 0.26. So we're passing in different values, but other than that, these sections here are exactly the same. And whenever you see that in your shader, that's a clue that you may be able to combine some things to save some performance. So here, and the other clue that you can see is these pieces of the shader here are working on UV coordinates. And UV coordinates, if we go back to the discussion that we had about data types, UV coordinates are just two values, a U and a V. And we have a pipeline that's wide enough to fit 4 values. So what we can do is combine these two pieces together. The most expensive parts of the shader here are our multiply and our add. And granted, those are super cheap to do. But still, we're doing a multiply and an add here. And we're also doing a multiply and an add here. And so we're doing 4 math operations when potentially we could just do 2. And let me show you how to do that. So down here I've got a version that's a little bit less expensive. I have our time coming in, and then I have a constant vec4 value that has 0.34, 0.12, 0.13, and 0.26. So I've got all 4 of the values here combined into one node. So the result of multiplying this will be these 2 values in the X and the Y channel, and these 2 values in the Z and the W channel. So this output here is a float 4 instead of a float 2. So if I take my texture coordinates and I take my U and V and append it again, now I have another float 4 where U and V are in the XY, and then U and V are in the ZW again. So I'm multiplying once, and then I can add once, and then I can split these things apart. So my original UVs coming in are split apart into my RG and my BA. So basically I've taken all of this and combined it, and so it's just this now. So instead of having 2 multiplies and 2 adds, I just have 1 multiply and 1 add. So you can see if I take this and I plug it in, now I've got the exact same result over here. Well, hopefully, yeah. I've got the exact same result here, but it's doing it with fewer math operations. So anytime that you can combine data and pipeline it together, pack it in like I'm doing here, I've got 4 values instead of 2 and 2, and I've got 4 values instead of 2 and 2. So I'm packing things together. Anytime you can do that, it can result in some nice savings for you. All right, let's talk about our last example. And for this one, we're going to go back to the shader that we built with the basics of PBR video that I created a couple of weeks ago. So what you can see here is we've got a shader with a texture for the color, a texture for the specular, a texture for the roughness, a texture for the normal map, and a texture for the ambient occlusion. So we're actually sampling 5 textures. And one of the most expensive instructions you can do in a shader is a texture sample. So anytime you have multiple texture samples that are all using the same UVs, if you can pack those together into a single texture, that will save you a lot. So right now we've got a shader that's doing 102 instructions, and granted this is pretty cheap, but still sampling 5 textures is less than ideal. And so what I've done is I created this new texture, and we're going to take a look at the contents of this texture. I created this new texture by packing the specular, the roughness, the metalness, and also the ambient occlusion all into one, into the red, green, blue, and alpha channels. So let's take a look. Here is our Cobblestones ASMR, and that stands for ambient occlusion, specular, metalness, and roughness. So let's take a look here. If we look at just the red channel, that is our ambient occlusion map. If we look at just the green channel, that is our specular map. If we look at just the blue channel, That's our metal map, and obviously we're not using that because there's no metal on Cobblestones. And then finally, if we look at our alpha channel, this is our roughness. So we've packed all 4 of these textures into a single texture using the various channels, and that's something that's pretty easy to do in Photoshop. You can just paste a grayscale image into each of your channels. So let's come back here to our PBR Basics shader, and so again, it's an ASMR, where A is ambient occlusion. So I'm going to wire my red into ambient occlusion. My S is my specular, so I'm going to wire that into specular. M is for metalness, and I'm not using that one. And then alpha is our roughness, so I'm going to wire this into the roughness channel. And bingo, there's our new channel, our new shader, and it looks exactly the same because I'm using all of the same data, but you can see here now it's using 100 instructions instead of 102. And like I said, not all instructions are created equal. Texture reading instructions are the most expensive, and so if you can reduce texture samples, that's something that you should definitely do. So I've gotten rid of these 3 texture samples and replaced them with just 1. And if I actually were using metalness, I would be replacing 4 texture samples with 1. And that is an amazing optimization. You definitely want to pack textures together whenever you can. And we'll have some more videos in the future where I show some specific examples of shaders where you can do that. Okay, so today we talked about measuring performance and also some methods for improving and optimizing your shader. So measuring performance, we talked about the performance view mode, the shader instructions, and also trying to measure specifically on your target platform. And then for the performance optimization, we went over 4 methods: getting rid of stuff you're not using, refactoring your math, pipelining your data together, and finally texture packing. So I hope these techniques are useful and that you can go and apply them to your own shaders to do things that are more efficient than what you're currently using. See you in the next video. Thanks for watching.